Hello class, this is day 14. I'm going to give you a few examples from chapter 16. I've uploaded the notes for chapter 16, which I have freshly rewritten, and hopefully you can read them. You can watch the video. I tried to close up as much as possible, and I uploaded it in 4K, so it should be readable, especially on a television set. Also, you should watch the acid base playlist. I recorded it back in 2013, and it's got all the videos for chapter 16 and 17 of the textbook, which is what we should cover. Today I'm going to do problems from chapter 16. I'm just going to pick a few problems randomly out of the book and do them for you. But watch the playlist. It's got part 1, 2, 3, all the way up to part 7 or 8, I think. And it introduces acid-base buffers. I haven't mentioned buffers yet. That's chapter 17. The Henderson-Hasselbalch equation. All of that's in there. And you're expected to know that in university, or you're expected to have been exposed to that. Obviously, they're going to probably cover some ground. They're going to do some review. This year especially, they're going to have to do some review because this cohort is going to be seriously unprepared. But here, listen to me on this. There are people sitting at home right now doing nothing, or they're doing fake learning. You know, you heard of fake news? There's also fake learning. There's a lot of nothing going on. And this presents an opportunity for you. Now, I know marks are due April 23rd, so after April 23rd, you don't have to really do anything. But seize the opportunity, because when everybody else is walking, if you're the only one running, guess where you'll end up? At the front. And the universities are going to take note of that. If you're the one who's prepared, it's going to make you look good. So don't waste your opportunities. Keep pushing forward when everybody else is resting on their laurels, and you'll get ahead. All right, let's do a couple of problems related to chapter 16. The first section is about the autoionization of water. Problem number 1631. Let's look at that one. It says, at the freezing point of water, 0 degrees Celsius, Kw equals 1.2 times 10 to the negative 15. Calculate H plus and OH minus for a neutral solution at this temperature. Well, the premise of a neutral solution is that the concentrations of H plus and OH minus are equal. So what would be the concentrations of H plus and OH minus? Well, if Kw is equal to 1.2 times 10 to the negative 15 at 0 degrees Celsius, and we know that H plus concentration times OH minus concentration is the ion product for neutral water, for pure water, and it has to equal that at 0, then all we have to do is take the square root of that number to find out what the concentration of H plus and OH minus is at that temperature. Square root of 1.2 exponent negative 15 is 3.46. 3.464 10162 times 10 to the negative 8. And that's going to equal the H plus concentration, and it's going to equal the OH minus concentration at 0 degrees Celsius in pure neutral water. Let's do 1629 as well. It has just a reminder of the basic laws that surround acid-base chemistry. Just to refresh your memories, you know that the ion product of water at 25 degrees Celsius, the concentration of H plus times the concentration of OH minus has to equal 10 to the negative 14. We call that Kw. We also know that pH is equal to the negative log of the H plus concentration. We know that pOH is equal to the negative log of OH minus concentration. we also can say that the pH plus the pOH always has to add up to 14. That the Ka of an acid is the concentration of the products divided by the concentration of the reactants. It's always like that for equilibria. And that Ka times Kb is equal to Kw for an acid and its conjugate base pair. An example of that would be an acid would be acetic acid, CH3COOH, and its conjugate base would be the acetate anion, CH3COO minus. All right, so the Kb of acetate anion multiplied by the Ka of the acetic acid is equal to the ion product of water in our calculations. So let's now look, with knowing this, let's look at question 1629. It says calculate H plus concentration for each of the following solutions and indicate whether the solution is acidic, basic, or neutral. In A, the hydroxide concentration is 0.3045. If the OH minus concentration is 0.00045, they're asking acidic, basic, or neutral. Oh, we'll go a little further than that. This is clearly a basic solution, so we can say pOH is equal to negative log of 0.00045. That's going to give you a pOH of 3.35. So therefore the pH is going to be 14 minus 3.35, and the pH is equal to 10.65. So this is a basic solution. Next, if the hydroxide ion concentration is 8.8 times 10 to the negative 9. That's kind of a tricky question. But let's look how that works. What's that again? 8.8 times 10 to the negative 9. So 8.8 times 10 to the negative 9 molar. So given that OH minus concentration times H plus concentration in aqueous solution always going to give you Kw, or 10 to the negative 14, we'll see that the H plus concentration is actually higher than the OH minus. So it's actually an acidic solution. So 10 to the negative 14, so the Kw, the H plus concentration is going to be equal to Kw over OH minus concentration. So 10 to the negative 14 over 8.8 times 10 to the negative 9, which gives you and there's something I want to point out to you guys, because I see students do it every year, and I try to warn them, but I don't think anybody really listens. That's one of the occupational hazards of being a teacher. Most students, you know that thing about Charlie Brown, and whenever the teacher talks, all you hear is wah, 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 wah. Well, that happens a lot more than you realize. Students don't listen, they tend to tune out, and it's not because they're bad students or anything, it's just a natural human thing. That, you know, you're writing and you get distracted and there's a pretty girl sitting next to you, and one of the things I see happen the most often in the use of calculators is that students try to enter exponents and they do it wrong. There's a button on your calculator that says EXP. When you press that button, the calculator automatically loads up times 10 to the power, and it leaves the flashing cursor where you have to enter the number. So all you have to do is enter the power. So if I want to write the number 8.8 times 10 to the power of negative 8 in my calculator, I'll say 8.8, and then you see this button here? focusing. Anyway, exponent is right there. When I press that button, you'll see a little E appear. That means the calculator has written times 10 to the power already for you. Then all you have to do is write the power. So if I want to write 0.8 times 10 to the power negative 8, I press that EXP button. When you see that letter E appear, or sometimes in some calculators you see a little tiny 10 with and then the cursor will go into the superscript area, then you write the negative 8. That's what that looks like on your calculator. Some students will say 8.8 and then they'll say times 10 to the power of, and they'll press Y to the X button, and then you can do that, but what happens sometimes is for whatever reason students want to write the exponent and they end up writing 10 times the number, what happens is they'll press the exponent button and then they'll write the times 10 part and write Y to the X 10 to the negative 8. So they essentially multiply their answer by 10 without realizing it, and then they get a wrong answer. So beware of doing that. It happens more often than you realize because a lot of people don't know how to use their calculators. They haven't taken the time. Maybe they don't use it that often. So just a little tip to avoid a lot of heartache and frustration. So we found that the concentration of H plus is 1.13 times 10 to the minus 7. That's a very slightly basic solution. Let's find out just how slightly basic it is. Negative log of H plus concentration is 1.136 times 10 to the negative 7. Let's find what that gives us as a pH. So log of 1.136 exponent negative 7, and what you get is 6.94. So it's just barely acidic. Just to the left of 7, so it's a very slightly acidic, essentially neutral. Enough of that. Let's do something else using strong acids and bases. Boring. Let's do something a little more exciting. Let's go to the acid. Let's go to weak bases. I think I've already done some examples of that. 1675. Let's do problem 1675. And I remind you that my playlist, Acids and Bases, which I compiled back in 2013, has all the notes for all this written on a big board. So you can go through all the examples that you might get in a typical test. 1675 asks, calculate the molar concentration of hydroxide ions in a 0.075 molar solution of ethylamine. Kb is equal to 6.4 times 10 to the negative 4. Calculate the pH of the solution. Let's do it using the approximation first, and then we'll try it using the quadratic formula. And if I'm feeling adventurous, we can even try the iteration method. So it's ethylamine. Ethylamine, is it ethylamine? No, it's yeah, it is ethylamine. So ethylamine looks like this. This is number 1675. Ethylamine, when you put it in the presence of water, and dissolve it in water, it pulls a proton off the water, and you get ethylammonium. And that water becomes a hydroxide. If you start off with 0.075 molar solution of this, a certain amount of it is going to dissociate. Let's call that X. So at equilibrium, you're going to have 0.075 minus X. This is not important. This will be 0 initially, a small amount X will appear, and then equilibrium will be X. Same with the hydroxide. So that helps to set up your equilibrium expression. The Ka value, the Kb value, didn't finish, Kb is equal to 6.4 times 10 to the negative 4. And then that's going to be equal to the concentration of products over reactants. You don't include water because water is at a concentration of 55 molar. So the Ka values don't include the water because it's been factored out. So it's the ethyl ammonium concentration times the hydroxide ion concentration. We may have done this already or something like it, but it doesn't hurt to repeat, just to consolidate it in your mind. So that's going to be represented by x times x over 0.075 minus x. All of it equal to 6.4 times negative 10 to the negative 4. If we use the approximation method, because this equilibration only dissolves a small amount, not dissolves, only ionizes a small amount of water to form hydroxide, this minus x is actually a pretty small number. So let's just ignore it. Let's rewrite the expression without that minus x part and see where it gets us. So 6.4 times 10 to the negative 4 is equal to x squared over 0.075. This simplifies the calculation to x squared is equal to these two numbers multiplied, which gives you 6.4 exponent negative 4 times 0.075. And that gives you 4.8 times 10 to the negative 5. So x equals the square root of that number, and you get 6.928 20323 times 10 to the negative 3, and that equals the hydroxide concentration using the approximation method. So if you find the pH using that number, you take the log of that, and the pOH will be equal to pOH equals negative log of OH minus concentration. What you get is 2.16 as your pOH. If you want to report a pH, subtract it from 14 and you get 11.84. Now, let's see what we get if we use the quadratic formula. We'll just leave the pH in the little corner there. I'll write it up here. pH equals 11.84. Let's see if we get the same number using the whole quadratic formula. So I'll erase all that. Don't really need to know that there. Just remember, this is the equation. And I'll enter all the numbers into the quadratic formula. So because Kb is equal to 6.4 times 10 to the negative 4, and that equals to x squared over 0.075 minus x, we can turn that into a trinomial. 6.4 times 10 to the negative 4 times 0.075 minus x is equal to x squared. Simplify that down. Well, let's see what 6.4 times 0.075 equals. 6.4 exponent negative 4 times 0.075 gives you 4.8 times 10 to the negative 5 minus 6.4 times 10 to the negative 4x. All that equals x squared. So x squared plus 6.4 times 10 to the negative 4x minus 4.8 times 10 to the negative 5 equals 0. Now let's enter that into our quadratic function in our calculator. So we'll go to mode, enter equation, right? Lots of reflections there. Okay, we'll press equations. Then it'll say number 2 is quadratic, so we'll press 2, and now it has 3 entries possible. So the first one is the number in front of x, which is 1, enter. The second one is 6.4 exponent negative 4, enter. And the third number is negative 4.8 exponent negative 5, enter. And then it gives me 2 values. Here's the 2 values it gives me. And those are the 2 solutions to the quadratic formula. One of them is obviously impossible. Just double checking my numbers here. 0.075, yeah. And this one is at negative 7.255. 8938 times 10 to the negative 3. So take the log of that first number. So this is the correct one. This is not possible. You can't have a negative concentration. So go back to normal mode. Log of 6.615583938 exponent negative 3 gives you a POH. So this was the OH concentration. Okay, I should have said that equals the OH minus concentration. So the POH is equal to negative log of the OH minus concentration, which gives you 2.1794. So the pH equals 11.82. So the answer we get is very similar to the approximation method. It's not sufficiently different that it would justify using the quadratic form. I mean, the quadratic form. I still use the quadratic formula because I have a calculator. But if I had to choose to do the quadratic, if I didn't have that function in my calculator, I would just stick with the approximation, and it would not. Typically, if the amount of dissociated acid or base is less than 5% of the original amount, you're well within your rights to keep the approximation as a way of calculating. It's not a problem. Let's do one more. With some numbers in it. 16,118. There's a nice problem. It asks how many milliliters of concentrated hydrochloric acid solution, 36% HCl by mass with a density of 1.18 grams per milliliter, are required to produce 10.0 liters of a solution that has a pH of 2.05. So you may have to work with this one backwards. 10.0 liters of a solution that has a pH of 2.05. So pH equals 2.05. First of all, let's find the concentration of H+. H+ concentration of such a solution is going to be 10 to the negative 2.05. So whatever that gives us. So you get 8.9125. .0938 times 10 to the minus 3 molar. So that's the concentration of H+. Remember, HCl is a strong acid, so it fully dissociates, and we're going to make 10 liters of that solution. So to get that concentration, we have to find out how many moles. So we know that molarity is equal to the number of moles divided by the volume. So the number of moles is equal to molarity times the volume. The molarity is here. No, we want N by itself. So molarity is this. The volume is 10 liters. So N is equal to 8.9125, etc., times 10 to the negative 3. And you want 10 liters of that solution. So that's going to tell you how many moles of acid you need. Times 10 gives you 8.912509, same number. 38 times 10 to the negative 2, obviously, moles of HCl. Now, how are you going to get that many moles of HCl from a solution that is 36% HPl by mass if it has a density of 1.18 grams per milliliter? You're going to have to find out how many milliliters of the solution you need. That many moles of HCl is needed. And HCl has a molar mass of 1.00794 plus 35.4527 for the HCl. So you're going to need times 1.00794 plus plus the 35.4527, close the brackets, it gives you, you're going to need 3.24955.796 grams of HCl. But your solution is 36% by mass, HCl. So you're going to need, since it's 36.0, yeah, 36.0% by mass HCl. So to get that amount of HCl, you divide by 0.36. Okay, and I'll show you how that works. So divide this all by 0.36, and it'll tell you how many grams of the solution you're going to need. You're going to need 9.02654,989 grams of solution, which is 36% HCl. So if you have 9 grams of that solution and 36% of it is HCl, you get that many grams of HCl. So that's how we're working backwards. So we got that many grams of solution. They're probably asking you how many milliliters. Yeah, how many milliliters, and they give you the density of the solution. Density of the solution is, I'm going to try to do this without erasing too much. Density of the solution is 1.18. Yeah, density is equal to 1.18 gram per milliliter, and you want that many grams, so you're looking for the milliliter. So given that density equals mass over volume, and you want the volume, density times volume equals mass, and therefore volume is equal to mass over density. So you got the mass here, and you're going to divide it by the density, 1.18 gram per milliliter, and it's going to give you your answer in milliliters. So divide that by 1.18, and you're going to get 7.64961,855 milliliters. How many sig figs are we allowed? We're only allowed 3 sig figs, so 7.65 milliliters HCl solution. And voila, there's our final answer. You know what I'd like you to try? Try a couple problems for homework. Try 1676, and try you know what, I'll leave it at that. Just do 1676 and watch the playlist called Acids and Bases, okay? We'll see you tomorrow.